Welcome to our project on guided fault mapping. My name is Mindy Zuckerman.
My name is Maddie Schwartz.
My name is Abdel Hafiz.
My name is Aswai Jakodudu.
The scenario for our project is that geologists are interested in mapping a rocky fault scarp at very high resolution with a drone during a field investigation. A drone can fly over a scarp and map much faster, more accurately, and more safely than a human in the field. Geologists would like to map the scarp to create and analyze topographic and geomorphic metrics of the rocks along the fault. Ultimately, this will help them understand earthquake hazards and landscape building processes. The goal of the project is to use metrics computed off-board from the lower resolution data to plan the drone's path such that it follows the scarp's extent on its own without being controlled in real time. There are 3 stages to our workflow. First, DEM processing, then path generation in Python, and stage 3 is implementation of the path in simulation.
The first step in stage 1 of our workflow was generating a digital elevation model of the Bishop Scarp. We did this by taking the mesh present in Gazebo and converting it into a DEM using Cloud Compare. This slide shows a 3D visualization of the DEM in ArcScene and then in 2D as a map displayed in Python. The next step in our workflow is to compute the second derivative of elevation, which is slope. This generates a slope map, which defines the extent of the scarp. As you can see from the slope map on the right, the scarp is in the lighter green and yellow colors. Next, to extract just the scarp from the surrounding topography, we first applied a Gaussian blur to the slope map and then a k-means algorithm with only 2 classes. And so the darker red output from the k-means is the outline of the scarp itself. We then converted the scarp outline from a raster file format into a polygon. This is because the polygon format is geospatially referenced and is represented by a series of XY coordinates in space. And from that, we can compute the center line of the polygon, which generates a line shapefile format that is represented by points and XY space. And this is essentially a path of waypoints for the drone to follow while mapping. Here's a 3D visualization of the scarp polygon extent in orange, and each of the waypoints are these black dots.
All right, so the last stage in our project is implementation in RAS ArcMap. And here, as you can see, first we exported the center line that we already generated before into CSV file in order to import it into RAS, basically. And in this video, as you can see on the far right corner, the Q ground control showing the drones mapping the scarp from south to north, and then creating a loop after it done, creating the further north part of the scarp. And in the far left corner, you can see the generation of the 3D point cloud, which is not really good at this stage because we don't have the bottom depth sensor installed on our camera. And so the generation of point clouds rely only on the front camera sensor, front depth sensor. Right, yeah, I think that's about it.
Okay, so coming to the challenges phase, there are many approaches to extract waypoints. We have chosen the centerline approach, but we faced a problem regarding the DEM coordinates. The problem, like the coordinate origin, is with the mesh center, while the coordinates in Gazebo are centered on the drone. So we realized it and we have resolved the problem, and we could basically use the centerline points as planned. And to conclude, overall, this project, it shows the ability of off-core path generation, like from topographic metrics for UAV-based mapping systems. And the lessons we have learned from this project is like we need more practice operating in gazebo, and also we learned about adding trajectories in the path planning, which will be very good for that. Thank you.